Alright, let's talk about Artinian rings. So, we want to prove if you have a Noetherian ring A and a prime ideal P contained in A, then the localization at P is Artinian if... Why are the two F's like really weird looking? Probably just a fluke in the typesetting, but whatever. So, the localization at A... No, the localization of A at P is Artinian if and only if P is a minimal prime ideal. So to prove this, first suppose we're going to do the forwards direction. So suppose that you have the localization at P is Artinian. We know that in a Artinian ring, every prime ideal of the localization at every prime ideal of an Artinian ring is maximal, and so in particular we have every prime ideal of of this localization is maximal. So let's see here. Remember A sub P. This is S inverse A, where S is A set minus P. And then we've proven that there is a one-to-one correspondence between the prime ideals of the localization which do not intersect S and the prime ideals of... no. There should not be a localization there. There is a one-to-one correspondence between the prime ideals of the underlying ring, which do not intersect S, and the prime ideals of the localization. And the correspondence is given by the map. You take a prime ideal A, which does not intersect S, and you map it to S inverse A. Since P is prime, S inverse P is prime. P is prime in A, so S inverse P is prime in A in the localization. Alright, so we know that... Right, because P is prime, and it's just under this map. It's just the image under this map of that map. And certainly P does not intersect S because S does not contain any elements of P. Alright, so so this S inverse P, so we know P is prime, we want P to be minimal. So suppose we have minimal prime ideal. So minimal among the collection of prime ideals, not like minimal just among all ideals. Minimal with respect to the prime ideals only. So now suppose we have any prime ideal Q which is contained in P. Then the intersection of Q with S is going to be contained in the intersection of P with S, and we know that this is empty. And so therefore S inverse Q is a prime ideal. A prime ideal in the localization. That's because of our correspondence. But now, since that ring is Artinian, the localization is an Artinian ring. In Artinian rings, prime ideals are maximal. So in particular, S inverse Q is maximal. So... also, the fact that Q is contained in P implies that S inverse Q is contained in S inverse P. But look, S inverse Q is maximal, and so it must be that, well, either S inverse P is all of S inverse A, which is not going to be the case, because, if F inverse P is all of A, is all of S inverse A, then P equals A. And so then A localized at P, you're localizing at A set minus A. It doesn't even make any sense. Yeah, we can't even... No, this doesn't even make sense when P is equal to A. Alright, so, since S inverse P is not the entire ring, it must be Q. Because S inverse P is not all of S inverse A, it must be S inverse Q because of the maximality of S inverse Q. Okay, so now we have these two rings being the same, but now we have that one-to-one correspondence between the the set of ideals. So because it's a one-to-one correspondence, we can go backwards. And so the fact that S inverse Q equals S inverse P, we go backwards under this map here, and we get that Q equals P. So any prime ideal contained in P is precisely P, and that's what it means for P to be a minimal prime ideal. So that's the forwards direction. For the backwards direction, suppose we have a minimal prime ideal P. Again, we know the set of prime ideals not an intersecting S is in one-to-one correspondence with the set of prime ideals of the localization. So these are the prime ideals which are contained in P. But since P is minimal, the set of prime ideals contained in P consists only of the ideal P. Well, does it contain 0? Well, I guess that would be kind of dumb if it contained the 0 ideal, because then the only I think part of the definition of a minimal prime ideal would be that like minimal among the set of non-trivial prime ideals, because otherwise 0 is the only minimal prime ideal, and then it's not really a useful definition at all. It's not really interesting. Okay, so anyway, since P is minimal, the set of prime ideals contained in P consists only of the element P. But this is in correspondence with the prime ideals of the localization. And if there's only one element in the former, there's only one element in the latter. And given our correspondence map, which we have up here, the set in the latter, i.e. the set of ideals in the localization ring, is precisely S inverse P. Okay. Alright, so we want to prove that A sub P is Artinian. So we want to prove, let's see here. We know that a Noetherian ring of dimension 0, and I'll explain what dimension 0 means. And a Noetherian ring of dimension 0 is Artinian. So, basically we're going to get to dimension 0, and I think that just means every prime ideal is maximal. But, okay, so let's keep going. So, since P is prime, the localization is, well, local, and so it contains a unique maximal ideal. And since, okay, so why is S inverse P, okay, so we know that when you localize at a prime ideal, not only do we get a local ring, but we've proven that the unique maximal ideal is always given by S inverse P, where P is whatever prime ideal you were localizing at. So therefore S inverse P is the unique maximal ideal of the localization. So S inverse, in particular, S inverse P is the only prime ideal, and so that, since S inverse P is the only prime ideal, and since it's also maximal, we know that every prime ideal in the localization is maximal. That's what it means for the ring to be, or for the localization to have, the localized ring to have dimension 0. A ring has dimension 0 if every prime ideal is maximal. And here there's only one prime ideal, and we've proven that it's maximal, and so every prime ideal is maximal. Okay, so this localized ring has dimension 0, and also since A is Noetherian, we know that Noetherianity can push forward to localization. So the fact that A is Noetherian implies that the localization is Noetherian as well. So therefore, the localization is a Noetherian ring which has dimension 0, i.e. it's a Noetherian ring in which every prime ideal is maximal, and therefore those conditions are enough to prove that the localization is Artinian, which is what we were trying to show in the backwards direction. Alright, so for this if and only if we've proven forwards and backwards, and so then we're done with the proof, and there you go.